Hey there, grade 7 students, and welcome to today's Explainer. I am your master teacher, and let me tell you, today we are going on an absolutely fantastic scientific journey. We're going to uncover the mysteries of things that are just simply too small to see with our own eyes. You know, in science, we often deal with systems that are incredibly complex, way too enormous to grasp, or way too microscopic to observe directly. But as scientists, we never, ever let that stop our curiosity. Instead, we use our critical thinking to build bridges to the unseen.
All right, let's take a quick look at our roadmap for today. We've got 5 stops. First, seeing the unseen world. Second, types of scientific models. Third, the history of the atom. Fourth, the particle model. And finally, matter and motion. Let's dive right in.
Starting off with Section 1, Seeing the Unseen World, where we'll cover the basics of matter.
Okay, so if we want to study the invisible, we first need to actually understand what makes up the incredible world around us. So, let's define a totally crucial term, matter. Quite simply, matter is literally everything around us. The chair you're sitting on right now, the water you drink, the air you breathe, it's all matter. And all matter is composed of tiny fundamental building blocks. What's really cool is that every single pure substance out there has its very own specific kind of these particles.
Now, these tiny building blocks are called particles. Think of them like invisible Lego bricks that construct the entire universe. They can be individual atoms or molecules made of atoms bonded together. But here is the crazy part. Not only are they incredibly tiny, but they are constantly in motion. To put that into perspective, a single drop of water contains roughly 1.5 sextillion particles. That's a 1 with 21 zeros, and they never truly stop. Whether they're just vibrating in place or zooming across a room, motion is their absolute natural state.
So the way these tiny particles groove and move and how they space themselves out actually determines the state of matter. This is exactly why water can exist as solid ice, free-flowing liquid water, or gaseous steam. Believe it or not, it's the exact same water molecules in all 3 states, but their arrangement and kinetic energy, basically their movement, create entirely different physical forms.
Moving right along to Section 2, Types of Scientific Models. Think of these as our glasses for the unseen.
Because these particles are way too small to see, scientists face a really big challenge. How do you study what's invisible? Well, they use models as their scientific glasses to bring highly complex ideas into clear focus. There are 3 main types. First up, physical models. These are smaller, simpler representations of something, like a globe of the Earth. Scientists choose this when they need to safely study a physical portion of a much larger object. Next, we have conceptual models. These tie together different ideas to explain a phenomenon, kind of like a diagram showing the step-by-step life cycle of a plant. Finally, mathematical models. These are sets of complex equations, usually run on super powerful computers. Scientists use these to handle massive amounts of data, like predicting the future through your daily weather app.
Let's do a quick formative check right here just to make sure we're tracking together. Why do scientists rely on these models? Take a second to think about it. Well, if you said that scientists use them to test ideas and make predictions about complex systems that are just too difficult to study directly, you hit the nail on the head. You are thinking like true scientists.
All right, on to Section 3, History of the Atom. Let's take a little journey through time, shall we?
You see, scientific models are rarely perfect on the first try. They require incredible perseverance and generations of rigorous testing. Back in ancient times, a philosopher named Democritus first proposed that matter was made of tiny, indivisible pieces. His conceptual model was just a simple, solid sphere. Fast forward to 1897, J.J. Thomson discovered negative charges and gave us the plum pudding model. Then, in 1911, Ernest Rutherford found the dense center, giving us the nucleus model. By 1913, Niels Bohr organized those electrons into specific orbits. And today, we use the highly complex quantum mechanical electron cloud model. Every single step of the way, scientists tested past data against the present to keep improving their models.
Just think about the huge leap in critical thinking between these 2 eras. On one side, we have Democritus's ancient idea of an indivisible solid sphere. It was a really great start. But on the other side, thanks to modern equipment and advanced mathematical models, we have the quantum mechanical model. Here, electrons don't just sit there. They buzz around in a highly complex cloud of probabilities. This shows us an absolutely vital scientific lesson. Models definitely have limitations, but careful construction and continuous testing allow us to keep improving our accuracy.
Time for another quick quiz to check our understanding of that history. Think back to that timeline. What resembles the plum pudding model of the atom? Got it?
The plum pudding model is best described as a positively charged sphere with negatively charged electrons scattered throughout it, literally like plums scattered inside a pudding.
Now for Section 4, the particle model. We're going to look at Tom's kitchen experiments.
Let's shrink down to the microscopic level for a second and apply these scientific models to our everyday household routines. Picture this. Tom is making a cold iced tea on a hot summer day. The ice starts as a solid. The water molecules inside are tightly packed together in a regular pattern, just sort of vibrating in place. But then, the warmer summer air begins to transfer heat energy to those ice cubes. As the molecules absorb this heat, their kinetic energy shoots up. They vibrate faster and faster until they literally overcome the attractive forces holding them in that rigid structure. And the result? The ice transitions into liquid water, where the particles flow freely and take the shape of the bottom of the glass. It's happening right there in your kitchen.
Which brings us to Section 5, Matter in Motion. Welcome to the sneaky particle party. To really make this abstract concept stick in our brains, let's visualize the exact spacing and movement of these particles. Looking at solids, the particles are arranged in a specific, tightly packed pattern with very minimal space. For liquids, the particles are still close, but they've broken that rigid formation, giving them a lot more freedom to move. And as for gases, the particles have massive amounts of space between them, and they're zooming rapidly in all directions.
Okay, I want you to actually imagine acting this out with your classmates to build your very own physical model. To represent solid ice crystals, you and your friends would stand close together and link arms tightly to form a rigid structure. As the temperature increases and melting begins, you slowly wiggle and vibrate in place. Once you become liquid water, you break formation and move freely around the room, gently bumping into each other. Then, when you hit the boiling point, you take a big jump apart and move rapidly, like escaping steam. And hey, if you cool down, you just gradually slow those movements and come closer together again.
Let's test your memory from the party with one last formative check. What is the characteristic of solid particles as seen in its particle model? Think about linking arms with your classmates. The answer is, in a solid state, particles are arranged in a rigid structure, vibrating in place with minimal space between them. Fantastic job!
To wrap up this explainer, I want to leave you with a really profound thought to reflect on. How has learning about these atomic models changed your perspective on the everyday materials around you? And more importantly, how can understanding these invisible, shifting particles help us solve real-world problems? Because whether it's predicting the weather with mathematical models or understanding how ice melts to prepare for climate changes, the models we construct in science empower us to understand and shape our entire world. Keep asking those big questions, Grade 7, and never, ever lose that scientific curiosity. Thank you so much for learning with me today.